Okay, I guess maybe we can start. So welcome everyone to 130B, Quantum Mechanics. Let's get started. So today we'll continue to review some of the things and maybe start talking about cat and bra. So let me first review what we have learned last time. Last time we have started the introduction of quantum mechanics. We said that quantum mechanics is a physics theory about microscopic particles and things like that. So as physics theory, it must provide descriptions for quantum systems. And in quantum mechanics, we describe quantum systems by complex vectors. We use complex vectors to encode the information about the state of a quantum system. And in order to understand complex vector, we last time start with complex numbers. And let me remind you, complex number, you can add them and multiply them together. And then there's complex conjugation. Then we talk about linear algebra. So you put a lot of complex number together, you can form complex vectors or complex matrices. So last time we end at matrix multiplication. Well, we have already learned that last time we reviewed that matrix, you can linearly combine them, meaning that you can have two matrices and then multiply with different complex numbers and then add them together. So not only matrix can be added together, they can also multiply with each other. So when you have two matrices, like this A and B matrix, a two-dimensional array of complex numbers, when they multiply, they give you a third matrix, which is again a two-dimensional array. So by saying that these are matrices, we basically mean that it's a complex number indexed by two indices. The first index is the row index and column index. So when you have two matrices multiplied together, the new matrix element labeled by this row and column index is related to the previous matrix element by this formula, where you can see that the column index and the column index of the first matrix and the row index of the second matrix are identified, and then as k, for example, and then sum over. So that is the rule to compute the new matrix element given the two matrices. This k index is also called the index that is going to be contracted, or the contracted index, or the index to be sum over, or sometimes called the dummy index. The reason that it's dummy, because it is sum over, so it never appears in the final result. The final result will only depend on the index I and j, where I coming from the first matrix and j coming from the second matrix. Okay? So, and for this reason, because you need to sum over k, so it is required that the first matrix A must has the number of columns to be the same as the second matrix B's number of rows. If this column number and row number doesn't match, then it doesn't make sense to sum over this k, because you don't know what's the range to sum over k, right? So that's a requirement. When you multiply two matrices together, you need to make sure that the column number of the first matrix and the row number of the second matrix match. And when that is the case, you can write this on the matrix level, saying that there are two matrices A and B multiplied into C. So given this matrix multiplication, you can specialize this multiplication to vectors, because vectors are simply kind of a reduction of matrix. When the matrix is reduced to either a single column or single row, that becomes a vector. For example, we can have this matrix vector multiplication, which is just special case of matrix if you treat this as a multi-row single column matrix. And then the multiplication rule is again the same. It's like the new matrix element. Now, if a matrix multiplying a column vector, the result will also be a column vector. But the column vector has new components, where the new components is related to the old components by multiplying the matrix element with the vector elements and then summing over these dummy index or the contracted index. And then there's also a right multiplication. This is called left multiplication because the matrix is multiplying on the vector from the left-hand side. And then the right multiplication is matrix on the right. And then right multiplication applies to a row vector multiplied with a matrix, and the result is still a row vector. You can also have vector-vector multiplication, which is basically what we know as inner product. For example, you can have two vectors if the first vector is a row vector, second vector is a column vector, you can see the number of rows and number of columns here, and the numbers of rows here is the same. And then that's why you can multiply this vector together, and the result will be ui vi and sum over I. And the result will be a one-by-one matrix. But by saying one-by-one matrix, it's basically a scalar or a number. But you can also multiply the row and column vector in another way, which is called outer product. This is inner, this is outer. You can see the only difference is that you exchange the order between the row and column vectors. But in this case, you can see the index to be summed over is this, the column index of this one and the row index of that one, which is only one-dimensional. So in that case, it spans into a matrix. So in the first case, the result is a scalar, and in the second case, the result is a matrix. And the matrix element is given by, for example, the i's row and j's column is given by the i's row and the j's column from these two vectors, multiply them together. So these are the two different ways that the two vectors, column and row vectors, can be multiplied. And it is illegal to multiply, for example, two row vectors together or two column vectors together. There's no such thing because the number of columns and the number of rows between these two matrices, if you view them as matrices, they don't match. Okay? So that is how you multiply matrix and also matrix and vector multiplication. Any questions? Okay, so there's a very special matrix called identity matrix. It's related to a symbol called the Kronecker symbol. Identity matrix is a special square matrix, n by n square matrix, whose diagonal is all 1 and off diagonal is all 0. And we denote it as this 1 with a double line to indicate that it acts as a number like 1, but it's actually a matrix. So this identity matrix, if you view its matrix element, the i's row and the j's column of the identity matrix is given by the so-called Kronecker delta symbol. And this symbol is denoted as a delta, and then it simply means that it's a number where when its index I and j are equal, the number is 1. When they are not equal, the number is 0. That's exactly the rules that you write down this identity matrix, right? When the row number and the column, when the row index and column index are the same, that means that matrix element is on the diagonal, and on the diagonal it must be 1, otherwise it's 0. So there's a nice property of the identity matrix because if you try to follow these matrix multiplication rules, you can show that for any vector, n-dimensional vector, no matter it's a column vector, so when I write this left multiplication, matrix multiply from the left of the vector, that implies that this vector is a column vector, which is a single column. And if the matrix is multiplying from the right, that implies this vector automatically is a row vector, otherwise it doesn't make sense. So in either cases, no matter you multiply identity matrix from left or from right, the vector is not going to change. So that basically means if you expand everything in terms of component, so this U has a vector component Ui, and then either you contract the I index with the I index in the delta symbol, or you contract the J index with the J index in the delta symbol. No matter which way you contract, the result is still the same vector. So what this means is that when you see a delta symbol in the summation, what you need to do is you basically first, for example, in this summation, you are going to sum over I, and then there's a delta symbol involving this I index. And what needs to be done is that you replace every I in this left-hand side expression by J, because I will be equal to J. Because only when I equal to J, there's a contribution, right? When I doesn't equal to J, the whole thing doesn't contribute to the sum because of this delta symbol goes to 0. So for that reason, that you simply need to replace every I by j, and then remove the delta symbol together with the summation. It's like the delta symbol can can cancel the summation, but when you cancel the delta symbol with the summation, remember to replace every I, the dummy index, by the other index in the delta symbol, which is j. So that's explained. The first line here, the second line follow the same idea because now j is the dummy index. So what you need to do is to cancel the delta symbol with the summation, but remember to replace every j by I. So the result is ui. Okay, so that's how you use delta symbol to do summations. Questions? Okay, let me tell you a little bit more about how to do matrix algebra in Mathematica. It's very convenient. In Mathematica, you can type in a matrix simply in terms of this curly bracket. So, for example, A is a matrix which looks like this, 1, 2, 3, 4, 5, 6, 7, 8, 9. And what you need to do is it has 3 rows. And within each row, you type in the matrix element 1, 2, 3, 4, 5, and so on. So this is the A matrix, basically. And B matrix looks like this. When you type it in like this, and then you say matrix form, Mathematica will print out the matrix form, which looks like that. So this is our A matrix. This is B matrix. And then you can simply multiply these two matrices together. Okay. So first of all, you can do linear combination. You can, for example, A plus B. And in this case, if I let you look at A and B again, A and B, if you plus these two matrices together, it turns out that every matrix element is 10, right? It's obvious. And then you can also multiply them by alpha and beta. And Mathematica, the nice thing is that you don't need to substitute numbers into every symbol. Sometimes you can work with these abstract algebraic symbols, so it can also give you symbolic answers for this linear combination of two matrices. And if you want to multiply matrix together, what you need to do is A dot B. So A dot B is A matrix on the left and B matrix on the right, and that's the result. So usually matrix multiplication is much harder to do by hand than simply linear combination, right? So it's recommended that you can use Mathematica when you need to do matrix multiplication such that you don't make a mistake. And then you can also do B dot A, which is matrix multiply the other way around. And if you look at these results, these two results, they are not the same. So you can see these are two different matrices. And unlike multiplying two numbers together, if we have two numbers, 2 times 3 and 3 times 2, they are both 6, right? So if you multiply two numbers, the result doesn't matter. It's the same, which means multiplying numbers is commutative. You can exchange the order of multiplication, but multiplying matrices is not commutative. Matrix multiplication is non-commutative, meaning that in general, A times B is not the same as B times A if A and B are matrices. But in general, I mean, it can be there are some special matrices where they commute with each other, and then it turns out their multiplication doesn't care their orderings, but for generic matrix, it's not the case. Okay? So you need to always keep in mind in matrix multiplication, for example, in this example, the left and right multiplication, the two different orders, they do not give you the same result. Okay, so now let's look at matrix when it acts on a vector. I'm saying that matrix as a machine, that means matrix can be viewed as a machine that takes a vector and acts on it, meaning that multiplies on it and returns a new vector, which is what we just learned as a matrix vector multiplication. For example, you start from a two-component vector. Let's look at two-component examples, which is a two-component vector U, and then U can be acted by a matrix M such that it gives you a new vector V, which is related to U by matrix multiplying from the left on the vector. For example, the U vector is like this. It's a two-component vector in a two-dimensional space. So for now, I just assume that they are real vectors. Complex vector is similar. And then you have a 2-by-2 matrix, which looks like this. And this is the V vector. So if you look at this expression for a while, you will realize what this matrix does for any vector is simply exchange the first component and the second component of this vector. Because if you take this matrix from the left and multiply this vector, the second component will combine with this 1 and become the first component. And the first component here will combine with the lower corner 1 and then becomes the second component, right? So this is what this matrix is telling you about. So what happens is that whenever you have a U vector, after the action of the matrix is like a machine that takes one vector and gives you another vector, which is this V vector. And what happens is that the two component, X and Y component, let's say, interchange. So you can drag, actually, if you are using Mathematica, you can actually move this U and V along. So if U vector is like this, when you exchange X and Y component, it becomes another V vector like that. So if you drag these vectors around and take a look, what happens actually is it seems that there's an invisible plane along this diagonal direction that U and V vector are simply reflection with each other, to each other with respect to this diagonal plane, right? Because when you want to change X and Y component, it's like flipping these two axes. X goes to Y, Y goes to X. So that is like going, this line is not going to change, and then this is like the reflection plane. And then this matrix, what it does is simply reflects any vector U with respect to this reflection plane, and then to the other side of V. You can see this is, you can even exchange them, yeah. So it's the reflection, okay? So, this is one way of applying matrices. Let's look at another example where this M is like this. It's a 2 by 2 matrix. Well, what it does is that for a two-component vector, the first component will not change because of this 1, and the second component, because of this -1, will get a minus sign once you apply this, multiply this matrix on the vector. So whatever you have, basically copy the first component to V and then opposite or flip the second component. And what this means that its X component is not going to change, but the Y component is going from positive to negative and vice versa. So it's like you are keeping the X-axis unchanged and then flipping the Y-axis, right? If you're flipping the Y-axis, it's like a reflection with respect to X. So that's why if you drag these vectors along, you can see now the reflection plane, instead of on the diagonal, this matrix actually acts on the vector in such a way that the reflection plane is along the X-axis. So that's what I mean, that matrix is like a machine. Matrix can take a vector to a new vector. And in these two cases that we have just shown, what the matrix does is it sets a reflection plane and then reflect the vector in this two-dimensional space to a new vector with respect to that plane. But let's look at something more interesting, which the matrix not only can perform reflection, but also rotation. For example, this matrix actually performs a 90-degree counterclockwise rotation to every vector that it encounters or it multiplies on. So what happens here is that U has two components again, but if you look at this matrix element, the first component will basically goes to the second row because of this 1 here. And the second component will pick up this -1 and go to the first row, meaning that you take the X component and copy it to the Y component, and you take the Y component, flip it, and then copy it to the X component. This is what this matrix is doing. This matrix is essentially doing something that is like a combination of the first two matrices. So if you look at this, if you have an X component along the positive X direction that gets copied to Y, so that means X-axis gets rotated to Y, right? And then the Y component gets a minus sign and copied to X. That means the Y component along this direction gets rotated again by 90 degrees and then copied to the minus X direction, which is what this matrix is saying. So if X and Y axis are basically doing this rotation, then any vector that is represented in this space will all get rotated because the whole coordinate system is rotating. So if you look at these examples, you can drag them in Mathematica. So that's what happens. Whenever you have a U vector, the V vector will just follow U vector in a way that they have 90-degree rotation in a counterclockwise manner. Okay, so these are the examples where matrices can act on the vector and give you new vectors. Why do I need to talk about these matrix acting on vectors? Because that leads to a new concept called eigensystem of a matrix. For example, in the previous example, when you see a matrix acting on vector, the action can be very complicated. The action can involve, for example, reflection and rotations. And if you want to describe what's the action of the matrix on the vector, you don't want yourself to describe the action on any possible vectors and enumerate all possibilities. So that's why people think about maybe we can find a better representation such that we can only focus on those eigenvectors. So eigenvectors are special vectors given a matrix. It's a vector that when the matrix acts on that vector doesn't change its direction, but only gets scaled by a scaling factor, lambda. And then if for example, it's not always true that the vector gets acted by a matrix will remain in the same direction. For example, this is the matrix that we just talked about, which basically exchange x and y component. So if you start from a u vector and get a new v vector, they are not in the same direction, right? So this u, arbitrary u vector, is not an eigenvector. But there are very special vectors, which is represented in gray color here. Well, when the matrix acts on this u1 or acts on this u2 vector, what happens is that the resulting vector is still along the same direction, either along the positive same direction or along the negative same direction, such that it doesn't change its direction, but only change its scaling factors. So these two special vectors, there's only two such kind of vector in the whole two-dimensional plane, and then these two vectors are called eigenvectors because when the matrix acts on that vector, basically looks like a scalar multiplying the vector. And the multiplication scalar is called eigenvalue. For example, if I put my u vector along the u1 direction, I can't control it very precisely, but you can see the resulting v vector is along the opposite direction, which means that these, for a vector along this direction, the application of the matrix on the vector is simply multiply the vector by a -1 such that it goes to the opposite direction. But if my u vector is along this u2 direction, then v vector basically coincide and scale with it in the same way. So in that case, I have this eigenvector, and then the corresponding eigenvalue is 1. Okay? So eigenvectors are special vectors in a matrix system that doesn't change its direction. Yeah.
So for rotation matrix.
Yes, I'm going to talk about that. The eigenvalue will be complex. So, so here the eigenvalues are real. And then very quickly, another example, which is reflection along the x direction. Again, you can see there are two eigenvectors, u1, which again, along this y direction, the vector is in the opposite scale in the opposite way. This vector is scaled in the same way. So the eigenvalues -1 and 1. What about rotation about 90-degree counterclockwise? You can't find any eigenvector in this two-dimensional plane that is only that doesn't change its direction, because every vector, when you rotate, it basically the matrix rotate the vector, so it changed the direction of the vector. But if you go beyond this real domain, although I start from a real matrix, so this is a lesson to learn that it is not true that you start from a real matrix and all the eigenvector and eigenvalue will remain in the real domain. You may start from a real matrix, and the result is that the eigenvector, as I listed here, they are complex vectors. And then the corresponding eigenvalue are also complex eigenvalues. In this case, actually purely imaginary complex numbers. So why this rotation correspond to an I? Maybe you recalled that last time when we talk about complex number multiplication, we say that there is a very interesting fact that e to the I theta is a very interesting complex factor. When that multiplies on a complex number, that simply basically perform a 90-degree rotation. So this has something to do with that. So this complex number I, when the vector is scaled by a complex number I, it actually rotates the vector between real and imaginary parts. So in this case, the it's harder to visualize these eigenvectors because this eigenvector has both real and imaginary parts. So I'm drawing, for example, the first eigenvector has a real part along this direction and has an imaginary part along that direction. The first eigenvector simply forms a coordinate system in terms of its real and imaginary part. So now when you multiply this I, basically what I does for these complex numbers is rotate the real to imaginary part and imaginary part to real part by 90-degree rotation. So that's why if you start from an eigenvector which spans like a coordinate system, rotate by 90 degrees, it's like a counterclockwise rotation. There's another eigenvector in this case which has an eigenvalue -1, which minus I, which correspond to the other direction, the clockwise rotation. So this matrix actually has two kind of different rotations. Although when this matrix acting on the real vectors, it always rotates the real vector in a counterclockwise manner. But when this matrix acts on an imaginary vector, it rotates in the other direction. So that's why it has two eigenvalues correspond to the two different 90-degree rotation. Okay. So if you want to see more about this visualization of eigenvectors and eigenvalues, you can go to the lecture notes and click. This is a link which you can click. You can watch on YouTube. Okay, so I hope I have introduced the idea of eigenvectors and eigenvalues. So essentially, eigenvectors and eigenvalue, they form an eigensystem because every eigenvalue is associated with an let's say the other way around. Every eigenvector has an associated eigenvalue given the matrix. And then the goal, in many cases, is now I'm given a matrix. I want to find its eigenvectors and eigenvalue because they are very useful. They are those invariant vectors, invariant in the sense that its direction is in some sense invariant. So how to find these eigensystem, let's say. So if I have a matrix M, which is this 2x2 matrix, what you can do in Mathematica, let's try that. And then what you can do is you can use this command called eigensystem, which is a function. When you put M inside there, then it basically returns the eigenvalues and eigenvectors. So these are the eigenvalues. This is the first eigenvalue, and then this is the first eigenvector correspond to that eigenvalue. This is second eigenvalue, and the second eigenvector correspond to that. And you can verify that if you apply this M on these eigenvectors, for example, I have an example here. Now I just copy this answer because Mathematica told me that this 1, 0 is one eigenvector. If I multiply M on that, what happens is indeed this vector gets scaled by 3 and then becomes 3, 0. And the second vector, I was told that it's also an eigenvector. Let's try it. So when you apply M on this eigenvector, the direction doesn't change, but the vector gets multiplied by 2, and 2 is exactly the eigenvalue. Okay? And there's another thing is that any vector, as long as it's on the same direction, is still an eigenvector. For example, 1, 0. Okay, let me try another thing. Let's say 0.5 and 0, right? So instead of, I don't believe this answer, instead of 1, 0, I try another thing, 0.5 and 0. It turns out these two vectors are on the same line. So no matter how you scale the vector is still an eigenvector of M. Because when you apply M on this vector, you can see it becomes 1.5 and then 0. It still scales the vector by 3, right? So I think the reason is very obvious. Then, so the idea is that the eigenvector is actually not unique. You can even, not only 0.5, you can put another I here. Even you can go to the complex domain. You can scale this eigenvector by a complex number. The result is still it's still an eigenvector. It's still going to be multiplied by 3 times under the action of the matrix. So the choice of eigenvector is not unique. It's always up to like a global complex basis, and then or a global scaling factor. So you can always multiply eigenvector by generally non-zero complex numbers, and the result is still eigen. So for that reason, usually people want to normalize the vector such that wants to make the eigenvector unit length. Maybe there's some convenience associated with that. Okay, so this is how you find the eigenvalues and eigenvectors of a system. Okay, so any questions? Yeah, you can take a look at that YouTube video if you want to learn more about this linear algebra thing. So these are all the review I want to do for the beginning of our courses. One is complex algebra and linear algebra. So with that kind of preparation, we can start really talking about quantum states. Quantum states, as we said, are represented by complex vectors. So that's actually the first postulate in quantum mechanics. States of a quantum system is described as vectors in the associated Hilbert space. Hilbert space is a space of vectors, all the possible complex vectors form a space. Within the space, the vector can linearly combine with each other, so that spans the full Hilbert space. For example, previously, when we draw this vector in the two-dimensional space, then that two-dimensional plane is our Hilbert space. But in general, we will have a complex vector which of n dimensions, so this Hilbert space can be of very high dimensions. In quantum mechanics, every state is described by a complex vector, and then, in particular, a complex column vector. So we denote that as a cat. This is the cat symbol, and then this is a corresponding column vector in the Dirac notation, where every component in this complex vector is a complex number. And the length of this vector is the dimension of the associated vector space, or the Hilbert space. You may notice that I use a very funny equation, equality symbol, equal sign. It's not the usual equal sign, which is two horizontal lines. There's a bump here, right? This kind of equal sign simply implies that the vector representation is basis dependent. What do I mean by basis dependent? Basis is your choice of coordinate system. Even you have the same vector and choosing different coordinate system resulting in different ways of interpreting its components in the coordinate system. So the behavior, this kind of behavior is called basis dependent. When you want to, this cat V is an abstract vector. It's an abstract symbol of the vector. But when you want to represent it or write down its vector component, you need to tell me what's your choice of your coordinate system or the basis of your coordinate. And only with that kind of choice, you can write down all the components. So that's why these values may change if we view the same state in different bases. So that's why, in that case, I use a hump equal in order to indicate that the result following that is basis dependent. But maybe we don't need to worry too much about that for now. You just need to think that this cat symbol or the cat state corresponds to a column vector. And in order to write down this representation, we need to specify a set of orthonormal basis vector. So in a coordinate system, the basis vectors are basically unit vectors along all different directions. For example, in two-dimensional space, you may have x basis and y basis. So the x basis vector is like 1, 0, y is like 0, 1. And in higher dimensional space, you basically use this so-called one-hot unit vector. The name one-hot basically means that the vector is very cool everywhere, meaning that it's 0 everywhere. Only at one position, one vector element is hot, meaning that it's 1, basically. So 1 is hot, 0 is cold. So one-hot meaning that there's only one point where the number is non-zero, and which is actually 1. So one-hot unit vector goes like 1, 0, 0, 0, and 0, 1, 0, and 0, 0, 1, and so on. So you basically arrange this 1 in the first place, second place, third place, and so on. That corresponds to all your set of basis vectors, and which we usually label the basis vector by its index. This is the first basis, this is the second basis, and so on. Such that if you have a generic vector V, which has this vector component V1 and V2 and so on, you can basically decompose this V vector as a column vector as V1 times the first basis and V2 times the second basis as a linear combination of all these basis vectors. As you can see, if I multiply this vector by V1, then V1 goes to this place. and multiply this vector by v2, v2 goes to the second place. Now if I add all of them together, I simply obtain a vector whose first component is v1, second component is v2, and so on, which is exactly the vector v in its column vector representation. So any vector in the Hilbert space can be written as a linear combination of basis vectors using complex linear combination coefficient if we are talking about complex vectors. And then the vector component vi is simply the combination coefficient in front of the I spaces. And there's a principle called the superposition principle that any linear combination of quantum states of a given quantum system is still a valid quantum state of the same system. Because we say that every quantum state is described by a vector. And actually, this idea is also the other way around. Any possible quantum state in the, any vector, actually, also describe a possible quantum state of the system. So if you linear combine two vectors together, the result is still a vector of the same length, right? As long as it's a vector of the same length, it's by length I mean the number of components is the same, then that's the vector in the same Hilbert space. Then that's the state of the same system. It's just a different state, but of the same system, okay? So that's very interesting that in quantum mechanics, you can actually superimpose quantum state together. For example, a famous example is like Schrödinger's cat. Schrödinger basically imagine a situation where he can create a thought experiment such that a cat is in a superposition of life and death. Live cat and dead cat, of course, are two legitimate quantum states of this cat system, but you can also add them or subtract them together, and then the result is still a legitimate quantum state. So that's about superposition. So we have just mentioned this cat vector is a column vector. Actually, there's another concept called the bra vector. A bra vector is a dual vector of the cat vector. Every cat vector as a column vector has a dual vector called the bra, which is another complex vector, but it's not a column vector, becomes a row vector. They are related by the complex transpose, meaning that if the cat vector is a column composed of complex numbers, its dual vector will be a row vector. Well, you simply copy every component to this row vector, put it in a horizontal direction, while also remember to complex conjugate every vector element. So that's the rule. Just accept that. That's the rule. So that's how you create this dual vector from bra vector from the cat vector. So by duality, meaning that duality means that there are two different things that actually encodes the same amount of information. So for a quantum state, you can either describe it by a cat vector or by its dual bra vector. It's not going to give you any difference. It encodes exactly the same amount of information, because if you ever encounter bra vector, you can recover the cat vector as well. You just need to copy every vector element into the column and then take a complex conjugation again, right? Complex conjugation, if you do it twice, it becomes do nothing operation. So you recover the same complex number if you complex conjugate twice. So the name of a bra and cat comes from the fact that they combine into a bracket, which we will introduce later. So you can actually inner product the bra vector and the cat vector together. So this inner product or the scalar product is called a bracket. And it is because people want to use this bracket to basically write down scalar products. So people create this bra and cat simply from these words, split this word into bra and cat.
I have a question.
Yes?
Where does the C come from?
So this C means that there's a complex number you can multiply, something like that. So don't be too picky about that. So every basis vector also has a dual basis vector. So previously, we say basis cat vector is a column one hot vector, and its dual vector is also a column, it's a row vector, but it's also one hot row vector, represented in this way. So any bra vector, again, can be written as a linear superposition of all these basis vectors. Remember that these basis vectors are row vectors and one hot. So that's why when you linearly combine them with V1 star and V2 star, it simply multiply V1 star, V2 star, and so on to the first, second, and third component, and so on. So when you add them together, again, you get a row vector as we seen just before as a bunch of these Vi star components put together. So this is another way of writing down the bra vector as a linear combination of its bases. You can see when you write down the explicit vector representation, I use this hump equal because the way that you represent this basis vector depends on the choice of basis. Actually, the way you represent even the vector depends on the choice of basis. But the fact that this vector is such a linear combination of these bases doesn't depend on how you choose the coordinate system, because once you specify the basis, anyway, the vector is a linear combination of these bases in this manner, no matter how you rotate the coordinate system, because when you rotate the coordinate system, the representation of each basis vector is going to change, but this representation of the vector is also going to change in a covariant manner, so such that this relationship of this vector, how it decomposes into the basis, doesn't change. That's why in quantum mechanics, we like this way of writing vectors more because it's basis independent. Okay, so this is the bra and cat vectors. So now let's look at the example. The example is a qubit system. What is a qubit? Qubit stands for quantum bit. Quantum bit is the fundamental information processing unit in a quantum computer. So a quantum bit is a quantum system that has two distinct states. And then just like a classical bit in our computer, which stores information, right? When you use computer, information is stored in these 0 and 1s in the memory of the computer. So for quantum bit, it's also the same idea. You have two states called 0 and 1, and you can choose 0 and 1 to be such a basis vector because because it's a two distinct states, which means the Hilbert space, vector space, has two dimensions, and then there are two orthogonal bases, and then you can basically represent 0. In this case, I'm not labeling by 1 and 2. Usually, I need to say this is the first basis and the second basis. But this name that you give to the vector is just a naming convention, right? So for the qubit, we usually say this is the 0 vector, this is the 1 vector, the two bases. So this vector representation of a quantum state is called the state vector, and then by saying it's a two-state system, meaning that its state vector has two components. So a generic quantum state of a qubit can be always written as a complex linear superposition between these two basis states, 0 state and 1 state. And as a result, the vector will be a column vector with two complex components, psi 0 and psi 1. So this is the generic qubit state. And conversely, every two component complex vector also describe a possible qubit state. But now you may wonder, what's the meaning associated with this complex number? Why do we need to encode the information in this way? It turns out that there's an interesting statistical interpretation in the sense that psi 0, if you take an absolute value, this is a norm absolute value or modulus square, and then psi 1 absolute value square. These two numbers, you can see they are all positive numbers. They respectively correspond to the probability to observe the qubit in the 0 state and the 1 state. So that is the statistical interpretation of these numbers. Although I haven't said that what is the physical meaning directly associated with this complex number, but it turns out these complex numbers, absolute value square, has probability interpretation. They basically correspond to the probability that you observe the qubit in 0 or in the 1 state. You can also write down its corresponding dual vector, which is very simple, which is just flip everything to the other way around. But always remember, put a complex conjugate on every complex number you ever encounter during this dual operation. For example, because the vector components, for example, if you go from column to row, you need to complex conjugate the vector component. So in this linear combination formulation, you also need to complex conjugate the superposition vectors, superposition components or coefficients. Okay? So this bra vector encodes the same information about the qubit as a cat vector. They are equally good description, but they play different roles in defining scalar product, as we will soon discuss maybe next time. So as a summary, immediately scalar product. Oh, we still have 6 minutes. Any questions? Okay, so what we have learned today is that quantum state can be described by vectors, either cat vector or bra vectors. Cat vector is a column vector, bra vector is a row vector. They are due to each other in the sense that they are related by transpose followed by complex conjugation. Any vector also represents a state of the quantum system. So maybe 5 minutes we can take a brief overview of a scalar product, which is all the reason that we need to introduce cat and bra. Suppose I have two vectors, both as cat vectors, column vectors, and then you can actually define the brackets. Brackets, as the name implicates, it's a brat and cat. It's you put the bra vector and the cat vector together, and then if you put these two vectors together, bra vector is a row vector, cat vector is a column vector. Put the row vector in front of the column vector, automatically you imply that you are going to do this matrix multiplication. And as we know that you can multiply a row vector with a column vector following the rule of matrix multiplication, and the result of that is basically U1 star V1 plus U2 star V2 and so on, summing over this component I, basically. Oh, sorry. This should be U and V, not V and W. And then I copy from previous notes. And yeah, this should be U and V. Okay, so that's the definition of scalar product. And as you can see, if you have two vectors, the result of the scalar product is a number, right? Because U star, Ui star and Vi, they are both numbers, and then multiplied together still a number, and summing over these complex numbers still a complex number. So scalar product has some very interesting properties which you can verify by yourself as an exercise. Not homework, you don't need to submit. So for example, one thing is that if you interchange U and V, for example, V and U, if you try to put V there and U the other way, you can show that what happens is that the star goes from U to V, right? V will get starred, but U will not get starred. But the result basically is the complex conjugate of this one, because if you take the complex conjugate of this complex number, the complex conjugate go to the every term in the summation, and then if you have two complex number, and then take a complex conjugate each one of them. So that's why VU inner product is the UV inner product with a complex conjugation. And then if you take the any vector and take the inner product or scalar product with itself, then that becomes the basically you are calculating the norm of this vector or the length of this vector, so this result will be greater or equal than 0, because now you will be Vi star and Vi. And we know that Vi star Vi simply is like V absolute value square, which is positive, at least non-negative. So if you sum over a lot of non-negative number together, the result must be non-negative. That's why this VV inner product or scalar product must be greater or equal than 0. And more specifically, this inner product will only be 0 if every vector component in V is 0. Otherwise, it will always be greater than 0. And then this actually simple fact implies that there's an equality, which means that the inner product between the scalar product between two vectors, and then if you take absolute value square, will always be less equal than the scalar product of these two vectors by themselves and then multiply together. If you want to see its proof, I'm not going to prove that. You can go to the Mathematica lecture notes. Just in the last minute, I show you a magic. You click on this, little button, and then it will expand the lecture notes into a proof of equation 59. If you don't want to see them again, you click that again, so that goes away. So this is how you can use this notebook by going to every exercise and click it. And that's it for today. Thank you. Yeah.